Now, if we know the constraints on our region, or the boundaries of our region, in terms of polar coordinates, rho, theta, and phi, and if we, of course, know the volume increment being a box defined by some change in rho, some change in theta, some change in phi, a delta rho, a delta theta, and a delta phi, it would turn out that that box had dimensions delta rho by rho sine theta, rho sine phi delta theta by rho delta theta, or delta phi. I'm not saying them right. But if we take delta rho times rho sine phi delta theta times rho delta phi, we get our volume increment then, the dimensions of our box, rho squared sine phi delta rho delta theta delta phi. Just taking the product of these three sides and putting them in the usual order. Okay? Now, it tells us that the volume, and I've got the word area written here, or I should have the word volume. Okay, this says area, and we're really talking about volume. I didn't do that in class, I just wrote that in there because I decided to identify what we have here, and then I went and misidentified it. Okay, the volume of the region bounded by these inequalities, okay, bounded by these conditions here, rho goes from 2 to 4. The constraints on rho, the limits on rho, don't depend on theta or phi. Okay? Limits of theta, pi over 2 to pi, they don't depend on rho or theta or phi. Limits on phi don't depend on rho or theta. So that we can do this integral in any order we want. Now, I'm not going through the steps of setting up a Riemann sum and talking about what this really means. Okay? I urge you to do so if you want to understand what's going on here. That's the optimal thing to do. Otherwise, you're just kind of more or less faking your way through it, although you can have significant knowledge and fake your way through with significant knowledge. That's par for the course. But optimally, you'll understand how the Riemann sum is set up and how it approaches this limit. Okay, the volume then is going to be the integral from 2 to 4 with respect to rho, from pi over 2 to pi with respect to theta, and from pi over 6 to pi over 4 with respect to phi of the volume increment. Okay, which is going to, in the limit, become rho squared sine phi d rho d theta d phi. Now that's an easy integral. Okay, antiderivative of sine phi is the only thing other than a polynomial or constant, or a power function or constant. And we're going to have to find the antiderivative, which is negative cosine phi, and then we've got to subtract the negative cosine of pi over 3, of pi over 6, from the negative cosine of pi over 3. Now the cosine of pi over 6 is bigger than the cosine of pi over 3, so it's a good thing we have a negative cosine, because that way this comes out positive. And if you don't understand what I just said, you need more work on these integrals, but at this stage I expect you do. Work out the integral. Okay? Antiderivative of rho squared is going to be rho cubed over 3, so you're going to have 4 cubed over 3 minus 2 cubed over 3. Okay, that's 64 over 3 minus 8 over 3, 56 over 3. Theta just goes from here to here, and we just get theta when we integrate. So we're going to then have that times pi over 2. And then we're going to have the difference in cosine between pi over 6 and pi over 3, the negative of that difference. And the cosine takes values 1/2 and square root of 3 over 2. So it's a square root of 3 minus 1 over 2. Multiply that by the pi over 2 you get here, and the 56/8 you get here. Well, you want to test me? Check that out. I might or might not be right. I think that's the way it works out. Okay. Well, anyhow, that's very straightforward. That's the volume integral. Okay, well, that's not, I mean, that's interesting enough. It's very neat that we can get the volume of this thing, and you ought to sketch this thing. I haven't sketched it today. Sketch it, see where it is, see what it looks like. But it gets more interesting if we give things a density. Okay, so in this case, I'm going to assume a density that's equal to 1 plus z. Now you say, what the heck is z? This is in spherical coordinates. Well, z, the spherical coordinate system is set up on an x, y, z coordinate system. It's just that we're using rho, theta, and z. Z is what? Well, if you cut the xyz plane with any plane that includes the z-axis, you're going to have something that looks like this. And if you cut it with a plane that's parallel to the z-axis, that includes the z-axis, and goes through the point that you're looking at, the point rho, theta, phi, which would be this point, chalk sticking, so that theta didn't come out very well, but there it is. Rho, theta, phi, that's this point. Okay? Theta, you're not sure of. Remember, you can cut this thing through any plane through the z-axis. You just cut it through the one that also goes through the point rho, theta, phi, so you're going to be cutting at an angle theta with respect to the x-axis. So if we have this line down here in the xy plane, the plane that includes this line and the z-axis, in other words the vertical plane through this line down in the xy plane at angle theta, will include the point rho, theta, phi, won't it? Since the theta coordinate here is theta. So we cut it with that plane, and then we look at the two-dimensional cut that we get. It includes the z-axis because we cut this thing with a plane that included the z-axis. It includes the point rho, theta, phi. And phi is the angle from the z-axis to our radial vector. And rho is the length of that vector. So here's what we have. Now, what's your z-coordinate? The z-coordinate is just the projection of this thing onto the z-axis. And if you look at this triangle, it's clear that that projection is z equals rho cosine phi. Okay, here's phi. This side here is your z-coordinate, and it's adjacent to the angle. And rho is the hypotenuse, so z is rho cosine phi. So that if the density is 1 plus z, that's not going to do us any good with this description, with this description of the region. But if we express it as 1 plus rho cosine phi, it is. Then we reason out that the typical volume increment, where we have a rho star and a theta star and a phi star, will have a mass equal to the product of the density and the volume. The density is going to be 1 plus rho star cosine of phi star. The volume increment is going to be rho star squared sine theta delta rho delta phi delta theta. We're going to sum all that up, and it's going to approach this integral where we just have the 1 plus rho cosine phi multiplied by our volume increment rho squared sine phi d rho d theta d phi. Now there are reasons why that's the limit. There are reasons why that works. You should understand them, ideally. But that's the way it works out. The limits in our integral, the region's still the same, so our integral is going to have the same limits. Okay, well, this integral, remember that this in an increment is just the mass of that increment, its density times volume. So when we do the integral, we add up all those densities times volumes, getting the total mass. So that's the mass of our region. Mass of the region. What region? The region described by this, where this is our density function. Okay, well, we can also do a moment of inertia. Okay, the moment of inertia about the z-axis, well, let's save that for another video because this one might be getting a little bit long, and I wanted to go on, but I'm going to stop and just come right back, and we'll talk about moment of inertia.